And you're here for it. I'm impressed. I am impressed. I am impressed. So, let's see. What should I say? I have decided that wherever I finish today is where the material for the exam next week will stop. So this will be the end of the material today, which means I'll get as much as I possibly can in between now and then. You want to hear it again? I said, you want to hear it again? Yes. No, so we're actually in pretty good shape. So I looked over where we are. In fact, where we are, we've covered the citric acid cycle. And I think I've made all the points there that I wanted to make. The only thing I was going to show you, and again, this is just for your information. You don't need to know this, but there's a table that shows the energetics, and these are the delta G0 prime values for each reaction, as well as the delta G0 prime for the overall reaction if you add them all up. And you can see that energetically, it's a very energetic process. It's very exergonic. It's releasing energy. The more this cycle turns, the more heat is going to be generated, the more NADHs will be generated, and the more GTP will be generated from that one reaction that generates GTP, and FADH2 as well. So we saw that one reaction I told you that was an energy barrier right there, and it's followed by a reaction right there that's energetically very favorable. So the combination of these two reactions, Gesundheit, is if you add those up, there's plus 29, there's minus 33. They sort of cancel each other out. So one can pull the other reaction. That does actually happen. Okay. There's a thing on here that I show that has the control of the cycle. But the reality is that the only thing that we really worry about with respect to control of the cycle is the amount of NAD and FAD. Other things affect it, but the reality is they don't play a big role in controlling the cycle. It's NAD and FAD that ultimately control it. And that'll be relevant when I talk today about electron transport, because it's in electron transport where NAD and FAD are generated from NADH and FADH2. Okay? So that's actually what I want to talk about now. And I'm going to come back. I've already talked about mitochondrial structure, but I'll remind you of something I said before. I talked about the inner mitochondrial membrane and the matrix as the two most important components of the mitochondrion. We're going to talk a lot today about what's in the inner mitochondrial membrane. And a term I didn't give you, but I will give you, is that places where it folds in on itself, like you see here, form structures that we refer to as cristae, C-R-I-S-T-A-E. Okay? Cristae are infoldings of the mitochondrial matrix, and what they do is they serve to increase the surface area of the mitochondrial matrix. The more surface area we have of the matrix, the more things we can put into it. Because we're going to see that everything we'll be talking about with respect to electron transport and also with respect to oxidative phosphorylation, all of these components are embedded in the mitochondrial inner membrane. So these cristae allow the cell to have more surface area to incorporate more of these things into there. Okay. Now, the electron transport system is doing exactly what it says. It's transporting electrons, all right? And it's transporting electrons starting from either NADH or FADH2. So NADH and FADH2 are sources of electrons. Remember that they were produced in reactions where oxidation happened. It meant that those electrons were transferred to NAD to make NADH and transferred to FAD to make FADH2. I said that we had to recycle NADH back to NAD, and we had to recycle FADH2 back to FAD, and now we're going to see how that recycling happens. Right? So in the recycling reactions, what's happening is NADH is dumping off its electrons and proton onto a complex that I'll talk about. FADH2 is dumping its electrons and protons onto a complex that we'll also talk about. Okay? Well, once it's dumped its electrons and proton, or electrons and protons, they become NAD and FAD again. Okay? All right, so that's how the recycling happens first. Well, the electrons have to go somewhere. Electrons don't just get donated to something and disappear. They have to go to something. And so they actually travel through a series of molecules and complexes, and they ultimately are donated to oxygen to make water. It takes a couple protons to do that too. So the ultimate acceptor of the electrons is oxygen. And this is why, when I told you earlier that if the cell runs out of oxygen, it can't convert NADH back to NAD. Because if there's no oxygen to accept the electrons way down here at the bottom, then what's going to happen? Well, they're going to plug up here, they're going to plug up here, they're going to plug up here, and they're ultimately going to plug up here and here, and then there's going to be no place to dump electrons. So that's a very important concept, okay? A very important concept. Oxygen is the terminal electron acceptor. If cells run out of oxygen for a variety of reasons, all right, then this process will stop. And because you've seen that NAD is needed for both glycolysis and for the citric acid cycle, those processes are going to stop unless we have other ways of making NAD. Well, you saw in glycolysis that there is a way to remake NAD. What was it? Until it's Friday just before a 3-day weekend. It's called fermentation. Fermentation allowed the cell to remake NAD. That happens in the cytoplasm very nicely. But I have bad news for you. There's no equivalent to fermentation in the mitochondrion. So NAD, if this isn't going on, the citric acid cycle will not be occurring. If electron transport is not happening, if the cell runs out of oxygen, the citric acid cycle will stop. Because NADH will accumulate, FADH2 will accumulate, and NAD and FAD are needed by the cycle. So oxygen is really critically important. All right. Well, let's talk about the transport process itself. We can make this horribly complicated, and this figure even attempts to make it horribly complicated. And I'm in the business of simplifying. I know that doesn't seem likely, but it's true. I'm in the business of making your lives easier. Okay? Let's make your life easier. All right? This is what's happening. That doesn't look any easier. No. No, it's not easier. We've got to make it easier. Okay? Let's make it into some terms that you can understand very readily. All right? Here is NADH. This NADH was produced in the matrix of the mitochondria. Notice we're in the matrix down here. It was produced in the matrix by the citric acid cycle. And now NADH is accumulating. The cell needs to have some NAD so it can keep the citric acid cycle going. It dumps its electrons off into this monstrosity here, which dumps it off to here, which dumps it off to here, which dumps it up to here, which dumps it up to here, blah, blah, blah. Well, let's keep it simple with names at least. NADH2 dumps its electrons off not into this monstrosity. It dumps its electrons off into something we'll call complex 1. Complex 1. So NADH dumps its electrons into complex 1. Now, everything else that's in here is an electrical circuit. If I said I just put electrons in at this end of the circuit and I'm going to trace where the electrons go through the circuit, we're going to see that happen. All right? This is slightly mispositioned there, isn't it? Okay, well. Complex 1 has electrons. If it doesn't get rid of its electrons, everything's going to stop. So it's got to dump its electrons onto the next thing. The next thing it dumps its electrons onto is Coenzyme Q, CoQ. We don't give CoQ a complex name because it's a small molecule. It's not really a complex, in contrast to what I said earlier. It's not a complex. It's a small molecule. We'll see that as we go through the cycle, things alternate between big, small, big, small, big. Okay? Big, small, big, small, big. All right. Coenzyme Q accepts electrons. Coenzyme Q accepts electrons in pairs, meaning it accepts 2 at a time. And that's important because NADH has 2 electrons to give up. NADH has a pair. It gives a pair to complex 1. Complex 1 gives a pair to coenzyme Q. And coenzyme Q has the ability to hand them off 1 at a time. And it does. And that's important because complex 3 can only, the next complex, which is shown right here, complex 3, can only accept electrons 1 at a time. You're thinking, where's complex 2? Okay, I'm keeping it simple for you for the moment. All right? Complex 1 to coenzyme Q to complex 3. Complex 3 dumps it off to another small thing. This is actually a protein called Cytochrome C. You can call it Cyt C if you want to, CYTC. Okay? Everything from complex 3 forwards is 1 electron at a time. 2 electrons, 2 electrons, 1 electron, 1 electron, and finally, Cytochrome C delivers its electron to complex 4. Now, this isn't bad. Let's think about what I just told you. NADH dumps a pair of electrons into complex 1. Complex 1 dumps a pair into coenzyme Q. Coenzyme Q dumps a single electron at a time into complex 3. Complex 3 dumps a single electron at a time into cytochrome C, and cytochrome C dumps a single electron at a time into complex 4. At complex 4, we're nearing the end, guys, because complex 4 is going to donate electrons to oxygen. Oxygen is going to pick up electrons, it's going to pick up protons, and it's going to make water. The reason that you're breathing heavily when you're exercising is because you need oxygen to recycle NAD. That's why you're breathing heavily. Okay? Now, there's something else about this that's really critical to efficient use of energy. This is where the electrons go. Bang, 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 bang. Or maybe I should tell you about complex 2. All right? Complex 2 actually turns out to be very simple. I scared you. All right? Complex 2 is simple. Complex 2 accepts electrons from FADH2, and it just gives its electrons to coenzyme Q as well. So coenzyme Q can take electrons from FAD or from complex 1. I'm sorry. Coenzyme Q can take electrons from complex 2 or from complex 1. Sorry. Okay? Coenzyme Q can accept electrons from complex 2 or complex 1. With me? So FADH2 dumps electrons to complex 2. NADH dumps electrons into complex 1. And it's an electron pair as well from complex 2. Yes, thank you for reminding me of that. Okay? So now we've got ways to get rid of the electrons in NADH and FADH2. We regenerate NAD and we regenerate FAD. But hey, if we don't do something with this energy of this electrical circuit, if we don't capture the energy of this circuit, we have just thrown away all kinds of energy. Remember, oxidation was generating energy? It was transferring electrons. We're actually going to capture the energy of those electrons in this process. And that's the next thing I'm going to tell you about. How do we capture the energy of that? This is cool. Okay? Think back to when I talked about membranes. And I talked about the fact that one of the membrane proteins I showed you was the lactose pump. Anybody remember how the lactose pump worked? What the energy source was for the lactose pump? Protons. Very good. Proton gradient. More protons outside than inside. Protons wanted in, and when they came in, they brought lactose with it. Right? That proton difference, high concentration outside, low concentration inside, was a source of energy. Well, what complex 1, 3, and 4 do is cool. As electrons are passing through them, they kick protons out of the matrix. They create a proton gradient. So I'll repeat that. Complexes 1, 3, and 4 create a proton gradient as a result of the electrons moving through them. Okay? Everybody with me? We now have, as a result of the movement of the electrons, we have more protons outside of the matrix than we have inside of the matrix. Those protons want in. And also, by the way, to orient, you notice it says intermembrane space. This is the space between the outer membrane and the inner membrane. Little space between there. Okay? Those protons want in. Okay? They don't come in during electron transport. They come in during the next process I'll talk about in a little bit called oxidative phosphorylation. And that's where ATP will be made. So what we're doing is we're doing what I call charging the battery right now. We're charging the battery by adding electricity, and that electricity is creating a proton gradient. We will see that the proton gradient is what's used to make ATP. Everybody with me? So the electrons that are coming from NADH and FADH2 are passing through the electron transport system. That causes protons to get pumped out, creating a proton gradient. And then later, that proton gradient is going to be used to make ATP. All right? Everybody with me there? All right. Now, yes? Does complex 2 kick out protons? She's got my next point already covered. All right. So complex 2 does not kick out protons. Complex 2 does not pump out protons. What does that mean? That means that if electrons are coming from NADH, they're going to kick out more protons than if they're coming from FADH2. Right? Because FADH2 is bypassing complex 1. We're not going to get as many protons kicked out. And if we don't get as many protons kicked out, we're not going to make as many ATPs. All right? Now I'm going to tell you what's going to happen, although I'll show you what happens later. When we get to the process of oxidative phosphorylation, okay, we get to something that people call the P to O ratio, which you don't really need to know. I'm not going to ask you about that. But the P to O ratio tells you how many ATPs you make, all right, per pair of electrons. All right? If you get a pair of electrons that start with NADH, you get about 3 ATPs. And if you get ATPs from pairs of electrons that start with FADH2, you get 2. That's approximate, but that's roughly what you get. Okay? Those ATPs do not come from electron transport. They come from oxidative phosphorylation. But the energy for making them does come from electron transport. So in other words, the process of electron transport doesn't make any ATP, but it charges the battery so that the battery can be used later to make ATP. Does that make sense? Okay. You're getting this very well. Very well. Okay. Oh, boy, wouldn't you love to memorize all that? Nah. I just like to show it to scare people. All right. All right. Are you suitably scared? All right. You know, there's actually some pretty cool stuff that's up here. And I'm just saying this. You're not going to need to know this. But it turns out that electrons, if you think about a circuit that has to happen in a cell membrane, I mean, a wire is very easy to understand, right? You run a wire from here to the back of the room, and I can conduct a current from here to there. But imagine somebody said to you that you're going to conduct a current from here to there, and you don't have a wire, but you've got to use proteins to do it. Okay? How would you do it? Well, it turns out the cell figured out electrical circuits long before human beings ever came along and did them. The cell uses a metal, like you would use in a wire, and they use iron. And iron is capable of existing in, you don't need to know this, I'm just telling you this. Iron can exist in two forms, +2 and +3, the difference being 1 electron. It's the difference of 1 electron. So I can pass an electron to iron, it'll go from 3 to 2, and when it passes it on to the next one, it goes back to being 3. So that means that iron, if I have a series of proteins that are full of iron, they can pass sequentially a proton from one iron to the next iron, 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 and that's how that circuit actually works. Right? There's only one place where that's violated, that rule is violated, and it's at the very end when we get to complex 4, and we have copper instead of iron. But copper can also exist in two different charge states, +1 and +2. So the cell figured this out. I mean, it's pretty cool to look at the movement of those electrons through all that, resulting ultimately in the transfer of those electrons to oxygen. That's what's happening here. Okay, we can go back to needing to know the rest of the stuff. Okay, I let you off for a minute. All right. One of the things I talked about, this is a molecule I like to think of as the traffic cop. Okay. A traffic cop stands at a busy intersection, holds the hand up to stop this group over here and let this group over here pass through, right? When I went to India many years ago, I was very impressed with the traffic cops and the traffic situation, which if you're in a major city in India, at least at that time, was absolutely chaotic. I couldn't understand for the life of me how it worked. And one of the reasons I couldn't understand for the life of me how it worked was because of the following. They had traffic lights that nobody paid any attention to. Okay? But instead, in the middle of the intersection, they would have a cop who was, and the light would be this or that car. I said, why do you have the lights? Didn't make any sense, right? So anyway, maybe I'm a dumb American, so I guess I didn't understand. But anyway, the traffic cop was the one who really ultimately was controlling everything. And this traffic cop is Coenzyme Q in this process because we have two lines of traffic coming in. We have a line coming from complex 1, and we have a line coming from complex 2. Okay? What's that? I'm sorry, I just started here. So you have 2 electrons at each one, but it can only accept from one at a time. Okay? Now, students get very worried about this. Okay? Well, which one's it taking from, et cetera? And the answer is it's taking from both, but not in 4 electrons at a time. Keep in mind that we have hundreds or thousands of these in a given membrane. Okay? We like to think about this, and we talk about this as this one goes to this one, goes to this one, goes to this one. But in reality, in a given intermitochondrial membrane, we have thousands of these things. So one coenzyme Q might be taking it from complex 1 when the other is taking it from complex 2, right? So don't worry about this goes to that, goes to this. The only reason I show you this figure is to show you that I wasn't lying, that basically that coenzyme Q can handle either 1 electron at a time or 2. If you want, you can trace the electrons here. No, I won't expect you to do that. Okay? Okay. All right. That is, oh, actually, I want to tell you one other thing, and that's down here at the bottom. Okay? Respiratory inhibitors. All right? I'm going to come back and talk about oxidative phosphorylation in a second. What you see on the screen are some interesting molecules. All right? They're labeled as respiratory inhibitors, and specifically what they are inhibitors of electron transport. They can stop the movement of electrons through complexes. Okay? The first one is called rotenone. Rotenone is a plant product, and it has a pretty big effect on insects. It's actually used as an organic insecticide. You can actually buy rotenone in a garden store and sprinkle it on your tomato plants. Okay, people do that sometimes to stop insects from eating the tomato plants. All right, it works by blocking the movement of electrons through complex 1. So if you stop the movement of electrons through complex 1, you're going to have a pretty drastic effect on cells because NADH cannot easily be converted back to NAD. FADH2 can be converted, right, because complex 2 isn't blocked, But complex 1 is blocked. Rotenone doesn't have a very large effect on humans. It would in high enough concentrations. But it has a very pronounced effect on insects. Okay? Antomycin A, another one that inhibits complex 1 is amytal. Amytal and rotenone both will affect complex 1. Okay? Another one that affects the complexes, and it's more poisonous to us than rotenone is antomycin A. Antomycin A will block movement of electrons through complex 3. If I block movement of electrons through complex 3, then I block movement through complex 1, and I block movement through complex 2 because I've put a dam in place down here and nothing is going to get past complex 3, so everything backs up. Okay? Antomycin A will be fairly poisonous. There are actually a couple of ways to get around it, but it's not something you would want to have. Okay? Now, the most poisonous of the electron transport inhibitors are those that block complex 4. Because when they block complex 4, there aren't any electrons that are going to move because it'll block complex 3, it'll block 2, it'll block 1, it'll block coenzyme Q, it blocks everything because I put a dam at the very end. Nothing's going to make it to oxygen. Those electrons are going to stop. The complex 4 inhibitors are some of the most poisonous substances around. They include cyanide. Cyanide inhibits complex 4. Carbon monoxide inhibits complex 4. Did Dr. McFadden talk about carbon monoxide with respect to hemoglobin? Maybe, okay. It's been so long ago you guys don't remember, all right? Carbon monoxide is doubly poisonous for you because it blocks complex 4, and it also will displace oxygen out of hemoglobin. It binds in the same place that oxygen does. Okay? So carbon monoxide gets you two ways. All right? There's a third compound that blocks complex 4. It's called azide. You don't need to know that. It's called AZIDE. But it's also a very nasty compound that you would not want to mess with. Okay. Well, why do we have these compounds? First of all, they exist in, yeah.
Why would blocking or inhibiting electrons in complex 4 have a greater?
Okay, so the question is, why would blocking things through complex 4 have a greater effect than others? All right, let's go to here. All right, let's say I stop this movement right here. Then that means electrons, this is going to be full of electrons, which means this will be full of electrons, which means this will be full of electrons, this, and we stop everything. If I block complex 1, then I still allow complex 2 to bring electrons in.
What about like the difference between blocking at 4 and 3?
Okay, so 3 and 4, I didn't tell you the difference, but there's actually a way to use vitamin C to get electrons in past 3. It's not very efficient, but you could, it's not, blocking 3 isn't quite as deadly as blocking 4. But you wouldn't want to block 3, let's put it that way. Okay? All right. Everybody got this? Makes sense? So if I give a person cyanide, or I give a cell, maybe better a cell than a person. If I give a cell, it's not like a mass murderer here, right? If I give a cell cyanide, what's going to happen to its citric acid cycle? There's a good exam question for you. What would happen to its citric acid cycle? It would stop. And the reason it would stop is NADH concentration would accumulate. That's how it kills you. That's how it kills you. Your citric acid cycle would stop. Glycolysis could ferment for a short period of time, but remember that you're only going to get 2 ATPs for every glucose in glycolysis, in fermentation, but you get 38 if you have oxidative phosphorylation going on. Yes? Is the fermentation faster? No. No. It just has to occur more often to make the same amount of ATP. But it's not faster, no. Okay? Everybody understand? Okay. So, this is cool. That's a respiratory inhibitor. All right? There's the blocks, etc. So there's other things on there. You don't need to know those. I want to tell you about something else that's relevant to this. And I don't see it on there. Why don't I have it on there? Okay. Well, there's another compound I want to tell you about. It's a miracle diet drug. I love to tell this to nutritionists. A miracle diet drug. You've heard this before. She's already laughing. Miracle diet drug? Yeah. Yeah. Whenever I hear the word miracle, it's like, okay, pull on the bullshit detectors, right? Right. Miracle diet drug. This one actually worked, and it does work, and there's a very good reason why it worked and why it does work. All right? This one was invented over 100 years ago. It's a compound called 2,4-dinitrophenol, and you can abbreviate it as 2,4-DNP. That's what most people call it, 2,4-DNP. All right? 2,4-DNP is a diet drug that works like they talk about in the email spam ads. People who took this miracle diet drug found that they could take it before going to bed, and they would wake up in the morning, and they would magically have fat burned away while they were asleep. I am not bullshitting you about that part. Wow, this is great, right? It's absolutely great. Isn't that what we all want? We don't want to have to go out and exercise to lose weight. We take a diet drug, we go to sleep. Hey, I can sleep with the best of them, right? And I wake up in the morning and I'm thinner. I can eat all I want. This is fantastic. And it's really great, except for it killed about 10% of the people that tried it. The other 9, I won't say they were okay, but the other 90 did lose weight. They lost weight. Okay. How did it work? Okay. Well, I told you that the electron transport is kicking those protons out of the mitochondrion, right? Out of the matrix. So we have a greater concentration of protons out than in. What 2,4-DNP did was it drilled a hole in the membrane. It drilled a hole in the membrane. So those protons that got kicked out came right back in. And if you didn't have a gradient of protons, you couldn't make ATP. It had the same effect as cyanide did, except for they were taking it in small enough doses that it wasn't knocking them off. Although about 10% it was knocking off, just like cyanide will knock them off. Okay? They were going to bed, and they were waking up in the morning, and they were warmer than they normally would be. Why would that be? This is a good exam question. Why are they generating heat? So let's think about this. You guys actually know the answer to this, all right? If I have no gradient, right, then as soon as electrons pass through, right, there's nothing to stop more electrons from coming through. So what's going to happen to the concentration of NAD? NAD concentration is going to increase, right? Because it's going to be constantly dumping off electrons into the complexes, and the complex is going to be racing electrons through as fast as they can, but nothing to stop them because there's no gradient. We'll see later that the gradient plays a role in that process, right? No, not friction. NAD concentrations increase. If NAD concentrations increase, what happens to the citric acid cycle? It goes like crazy. What happens to glycolysis? It goes like crazy. Both of these are very exergonic processes. What happens to the heat? Heat's going to go up. They get hot. All right? What happens to oxygen consumption? Up or down? It's going to go up. Right? So they're going to breathe heavily. They are going to generate heat. And if they don't die, that's how they're going to wake up in the morning. Now, at this point, I get the questions from somebody saying, well, what if you took just a little bit of this stuff? Just a little bit. All right? To which I say, what if you took just a little bit of cyanide? Or just a little bit of arsenic? You probably would lose weight. Right? So needless to say, this substance was banned by the FDA. Okay. Yes? It's a good question. Does the hole drilled in the membrane fix itself? And I don't believe it does. I think you actually have to grow new mitochondria. So that's why I said that those who survived weren't necessarily in good shape, but they were thinner. Yeah. Okay. So that's the sort of yin and yang of the blocking or not blocking, that is causing the other effect, letting the protons pass through, that causes problems. Well, let's look at oxidative phosphorylation, the time that we have left, to understand more about this ATP generation process. This is, oh, there's the uncoupler. I'm sorry, I knew I had it on there somewhere. It's right there. Okay. That's what 2,4-DNP looks like. No, you don't need to know the structure. Okay. But that little guy right there drills holes in your mitochondrial inner membrane. Okay. This thing that you see on the screen is one of the most amazing proteins that exists in nature. It's called ATP synthase. Okay? And this protein is responsible for making about 99% of the ATP in your body. This protein is embedded in the mitochondrial inner membrane. It's embedded in the mitochondrial inner membrane, and it's through this protein that the protons are moving. Protons move through this protein, and it's the movement of these protons through this protein that causes ATP to be made. All right? This is another view of it. Okay? To orient you, in this case, the matrix is on top, okay, and the intermembrane space is down here. Okay? Protons are in high concentration out here. They're in low concentration down here. They want to come through here, and what this protein provides is a channel for them to move through. Okay? This protein is called ATP synthase. It's also called complex 5, or complex V is the way it looks. It's called complex 5 or complex V, all right? Even though it has the word complex in it, it's not part of electron transport. This is a separate process called oxidative phosphorylation. Protons start here, they pass into here, and as they're passing through this little chamber right here, you see these little purple squiggles here? This is the magical part about this protein. This little set of purple squiggles, as the protons pass through it, rotate. They rotate. This is a cellular turbine. Okay? It's the movement of the protons through it that causes the turbine to turn. Well, we all know about how electricity is generated at a dam, right? You've got a wheel, you've got water that passes, makes the wheel turn, and the turning of the wheel turns a generator that creates electricity. Okay? Your cells figured this out long before we figured this out. This is, again, nature has its way of working. This turning turbine ultimately makes ATP up in here. So protons moving through cause the turbine to turn. If protons are not moving through, the turbine will not and cannot turn. So if I poke a hole in the membrane, no turning of turbine because there's no greater concentration outside than inside. It'd be like having the water on both sides of the dam be at the same level, right? I'm not going to make electricity. It's only when I have the water on one side higher than the other that it makes electricity, right? Okay. Now, how does turning of this turbine right here cause ATP to be made? All right? These guys up here, there are 6 proteins, all right? 3 identical units called alpha and 3 identical units called beta, and no, you don't need to know that. All right? They contain a binding site for ADP and phosphate. ADP and phosphate. Well, if you think about it, what does it take to make ATP? It takes ADP and it takes phosphate. So I've got one of these units here, and it's got ADP sitting right here. It's got phosphate sitting right here. They don't want to be together, right? They're negatively charged. It takes energy to make ATP. that energy has to overcome the negative charge of the ADP over here and the phosphate over here. And they're being held inside of one of these proteins. You got this all pictured in your head? Everybody with me? I see at least one or two frowns. Proteins. So let's say beta here has a binding site for both of these guys, ADP and phosphate. They're sitting there in this protein waiting to be put together. Haven't put them together yet, but they're just sitting here waiting to be put together. It's going to take energy to put them together. It's going to take energy to squeeze them together so that the bond forms between them, that high energy bond that's the triphosphate. How does that happen? Well, this rotating turbine down here is attached to this stalk right here. You see that stalk? No, I don't care if you know the Greek letters. That's not important. This stalk is turning. The turbine is turning. The stalk is turning. And as the stalk turns, it interacts with the proteins here and causes those proteins to change shape very slightly. When it encounters a protein that has an ADP and a phosphate, the protein changes shape and they get squeezed together. That is how ATP is made. This turbine turning is causing a protein to change shape, change the physical dimension so that the ADP and the phosphate get joined together. Okay? This makes 99% of your ATP. It makes 99% or more of the ATP on the face of the Earth. This is a nanomotor. We talk about nanotechnology. This is a nanomotor. It's a nanoturbine. It's a nanogenerator. You can call it a nano whatever you want, but it's very tiny, but it accomplishes exactly what I just told you. Everybody understand how that happened? You want to just say yes so we get out of here? Yes, question. Oh, very good question. How many protons does it take to make this happen? Okay. People spend entire lifetimes trying to answer that question. It takes a few. That's what it comes down to. No, I'm not trying to be flippant. There are arguments about how much it takes. It's probably on the order of about 7 to 10 protons to make an ATP. People spend their whole lives arguing about how many protons it takes, but the reality is it takes a few. We know it takes a few. Okay? Okay? It's not a 1-to-1 ratio, no. Yes? So good question. She says, can more than one ATP be made per one turn? It turns out that there are 6 proteins here. 3 of them have ADP and phosphate. Right? One turn will ultimately cause all 3 of those to compress. It's a little bit more complicated than that, but that's basically what's happening during a turn. Okay? Everybody with me? All right. This is a very, very cool process, as I said. Now, I've already shown you that. I've already talked about that, so we don't need that. That's kind of a dumb figure. We won't talk about that. And we've really got one more thing to talk about, and then we're going to call it a day. All right? I said there are 3 proteins there that can bind to ADP and phosphate. All right? The 3 proteins are identical, but their shape is dependent upon how that little rotor in the middle is turning. All right? So we can think of that little rotor as having a rudder. All right? So here's the rotor, and here's the rudder. And as it turns, that rudder is interacting with those proteins. Right? So this guy is spinning. I can't do my hand, that's why I'm doing my body. Okay? This rotor is interacting with a protein. Okay? That 3 steps that I just showed you are critical because the 3 proteins at any given time, each one's in a different configuration. Even though they're the same protein, they have slightly different shapes. If the rotor's pointing this way, whenever the rotor points to a protein, the protein makes an ATP. Well, I can only point to one of those 3 at a time. Right? The one I'm getting ready to point to is in the next configuration. It's already bound. So if I'm sitting here, I've made an ATP, the next one should be ready to make an ATP when I turn this direction, right? So this guy over here must be ready, sitting there with ADP and phosphate, okay, so that it can make ATP. You with me? This one just came from this one over here, and what it did was it finished making an ATP. And now it's gone to this one. All right? When this one points at a protein, that protein is what we call the T configuration, tight. All right? It's in that tight configuration that things get squeezed to make the ATP. All right? The one over here is in a loose configuration. It's waiting for this rudder to come along and do its thing. The one that's over here has finished making its ATP. It wants to get rid of it, so it's open. It lets go of the ATP that it made. Tight squeezes the ADP and the phosphate. Loose grabs ADP and phosphate and just holds on to them. Open lets go of the ATP. You with me? So this will go from T to L to O, to T to L to O. Okay? With me? That's what's happening in the synthesis of ATP. Questions, comments? Ready for a song to finish off the week? All right. Let me try to get it set up right this time. This is a song about what happens in your liver. What's that? And it's entitled In My Liver. It's to an old Beatles tune. Okay.